Okay. Getting down to the end, thankfully. So we only have 2 weeks left. So it means I have 3 lessons left to cover. And before we were dealing with the heat equation for quite some time. It's a parabolic PDE, and then we moved on to the wave equation, a hyperbolic PDE. We're going to finish up with an elliptic PDE, and that is Laplace's equation, and its close relative which is Poisson's equation. So this is going to be the only new material after test 2, and which I've finished grading, and the majority of people did quite well on that. And then so the final is going to be comprehensive. So certainly there'll be material from these last 3 lessons on Laplace's equation that I will cover, and then there'll be a sampling of problems similar to what you've seen on test 1 and 2 to round everything out. So as far as the length goes, we're talking 7 or 8 problems altogether, like we've had before. My plan is to compose the final this weekend. Now, but what I'm going to do for a practice test is I'm not going to make up a full practice test because a lot of this material you'll have been tested on before. So I will make practice versions of the problems on covering any new material on Laplace's equation, and then I will indicate to you which problems from the first 2 practice tests you should review. So basically, that makes up a practice test. Yeah, so you get to reach back and review some old things there. Okay. So let's get into these last 3 lessons and bring a semester to a close. So we'll be seeing lessons 31, 33, and 34. Okay, and that's the subject of a 9th and final homework assignment. I know I still have some lesson 8s to get graded. Please keep in mind for homework, there are 9 assignments in total. The lowest 2 get dropped. So if you've done everything up to this point, like homeworks 1 through 7, you could conceivably not do homework 8 and 9 at all. Okay. So today I'm going to be talking about the Laplacian. In any number of dimensions of the Laplacian, we've certainly seen this before, as it plays a key role in both a heat and wave equation. In one dimension, it's just uxx, but in general, it's the sum of all the second partial derivatives that are with respect to the same variable twice. So uxx plus uyy plus uzz. And it's a very important operator just because it comes up in all of the essential PDEs, elliptic, hyperbolic, or parabolic. So one thing I'll talk about today is how to interpret it. Okay. Actually, it's not just about 2 dimensions. Okay. All right. Now, for a simplest case of 1 dimension, where it's just, as I mentioned, uxx. Now, if I take a Taylor expansion of a function u of x around some point x naught, so we just have a first few terms right here. Now, what we'd have here, oh, that should be just u double prime, but that is the Laplacian of u at x naught. What I'm going to do is I'm going to take both sides of this equation and integrate it from x naught minus h to x naught plus h. So I'm going to integrate over an interval that is centered at x naught. Okay. So what happens when I do that? Okay. Now, in this case, so on the left side, I just have that integral. Can't really do anything with that to simplify it. Here, u of x naught is a constant. I'm integrating with respect to x, from x naught minus h to x naught plus h, but that's a constant. So then I just have the integral of 1 from x naught minus h to x naught plus h. The integral of 1 is just the difference of the limits, which in this case, if you subtract these two limits, the x naughts cancel and you just wind up with 2h. So I can just get 2h u of x naught for this term. For this term, again, u prime of x naught, that's a constant, so I can pull it out of the integral. So what I'm integrating now is just going to be what's left over, this part. And then here, u double prime is the same as the Laplacian in one dimension. So this part right here, all of that is a constant, so I pull that out as well. And then I have x minus x naught squared. That is still to be integrated. Now, these integrals, I can go ahead and evaluate them. To simplify matters, I'm making a change of variable, or you might think of it as a u substitution, where I want to map the interval from x naught minus h to x naught plus h to the interval from -1 to 1. So that would mean this change of variable. Now, why that's helpful is if I have an odd function, like an odd power of s, integrated over an interval from that's symmetric around 0, it's like it's -1 to 1, this integral is just going to be 0. So that part goes away. And also for this one, if I have an even function, it's like an even power of s integrated from -1 to 1, that's the same as integrating from 0 to 1 and then doubling it. So I get a factor of 2 here that cancels the 1/2 down here. This factor of h cubed comes about from it comes about from making the change of variable, because when I replace dx is replaced by h times ds, so I get a factor of h because of that, and then x minus x naught from this equation, that's equal to s times h, so it gives me an additional h squared that also shows up out here. So now I go ahead and integrate this. And I get the h cubed over 3 times the Laplacian at x naught. So now I've evaluated this as much as I can. And then I rearranged this. Because if I divide both sides by 2h, then this quantity here divided by 2h, that's the average value of u on this interval. Because remember, the average value of a function on an interval AB, you integrate it from a to b, and then you divide by the length of the interval, b minus a. The length of the interval in this case is 2h. So on the left side, I just wind up with the average of u on an interval. And then u of x naught plus h squared over 6 times the Laplacian. So what exactly does this tell us about how to interpret Laplacian is that if Laplacian is positive, then U is smaller than its average of its neighboring values. And this is easiest to understand in one dimension because Laplacian is just a second derivative. If U double prime is positive, that means the function is concave up, and that would mean that so based on how if you think of a graph of a concave up function, that the graph tends to fall below a secant line, so that so smaller than the average of neighboring values. If your Laplacian is negative, then U is larger than the average of neighboring values, and then if Laplacian is 0, then U is equal to its average. Okay. Now, what I showed you here was just one space dimension, but if you integrate over the disk for 2 dimensions or a ball over the interior of a sphere in 3 dimensions, then you wind up with the same kind of result. Okay. And I actually want to take a little time to show you that in 2 dimensions. Okay, so in 2 dimensions, I have U of, at some point, xy is U of, so I choose a center for my Taylor expansion. And depending on what class you've taken, you may not have seen a multivariable Taylor expansion before. So what we get is du dx times the change in x plus du dy times the change in y. Now, what about the second derivative terms? Because we have 3 distinct second partial derivatives, uxx, uxy, and uxy. So to include those terms as well. Okay, so here we have uxx. Whoops. Oh, I see what it's wrong. Okay. And here I have a factor of 1/2. Okay. Times a change in x squared. And then I have uxy times a change in x times a change in y. And then uyy times a change in y squared. Okay, and additional terms which I won't need here. The reason why only these have a factor of 1/2 is because really you have 4
Dr. Lambers, you're frozen. I'm not sure if you can hear this, though.
Well, that was fun. Can you all? Okay. So is video working? Okay. My laptop just crashed. I was just typing away, and all of a sudden, poof! It restarted. So, and then shortly after, when I see all these messages from y'all, like, "Is he frozen?" It's like worse than frozen. So, um, okay, I'm just glad that recording keeps going. Um, that might be fun for me to watch later. So, um, okay. Now, hopefully, my notes are intact. Oh, it looks like not entirely. Okay. Well, in that case, I'm definitely watching. Okay. All right. Yeah, so unfortunately, the last part of what I typed was lost. I guess it only saves every now and then. Okay, so I was working this out in 2D. Hopefully, whatever I type doesn't cause an issue. You never know. Okay, so I was dealing with the terms for the second partial derivatives. Okay, now I'm going to be a little lazy here. I'm going to assume that any partial derivatives that you see here are evaluated at x naught, y naught, just so that I'm not having to type out x naught, y naught so many times. Okay, so then we have uxx at that point times change in x squared, and then I have uxy times change in x, dang it, change in x times change in y, plus 1/2, dang it. Also, my typing ability, which is suspect to begin with, feels non-existent. Times change in y squared, and so on. Reason why only these terms have a 1/2 is that we really have 4 second partial derivatives: uxx, uxy, uyx, uyy. Uxy and uyx are equal under assumptions of continuity on the second partial derivatives. So those terms combine into this one. Okay. So now I have my multivariable Taylor expansion, and then what I want to do is integrate over the disk defined by x minus x naught squared plus y minus y naught squared is less than r squared for some circle that's centered at x naught y naught of radius r, and then we're just going to integrate over the interior of that circle or the disk. And I'll use polar coordinates where needed. So what that means is and I'm not just going to integrate them, I'm also going to divide by the area of that disk. So that would be, so I divide by pi capital R squared. That way, what I have here, okay, I'm going to call this disk D. Okay, so I'm taking the integral over D of u of xy dx dy. Okay, so now when I integrate all of this over the disk, well, u of x naught y naught, that's just a constant. So if I integrate that over a disk, I'm just going to get this times the area of a disk. But I'm already dividing by the area of a disk. So I'm just going to get u of x naught, y naught for this first term. Then for these two, ux and uy are both evaluated at x naught, y naught. Those are constants that can be pulled out of the integral. So now when I'm integrating over a disk, I'm going to switch to polar coordinates, and I will get integral of from 0 to r, 0 to 2 pi, and then from 0 to r, and then I have x minus x naught, and I'm going to find my polar coordinates. So x is x naught plus r cosine theta. Y is equal to y naught plus r sine theta. Doesn't take into account that the center's at x naught, y naught. So then x minus x naught is r cosine theta. And then I have r dr d theta from a change of coordinates to a polar. And then I'll have a similar thing for du dy. I hope I can fit it on this line. I'm just going to have sine theta. Okay. And then for second derivative terms, all the partial derivatives can be factored out. I can't forget to divide by pi r squared. Okay. And then same here for uxx. Okay. So here I'm going to have x minus x naught. That's going to be r squared cosine squared theta. Okay. And then similar for the other two terms involving second partials. Oh, that took up way too much room. Okay. Okay, uxy, no factor of 2. Here I have cosine theta times sine theta. Whoops, not that integral. Okay. Okay. All right, everything's in order. I need to include some spacing here. Okay. So now I'm evaluating all of these. But the thing is, here I'm integrating with respect to r and theta. But I have a function of r times a function of theta. I can separate these into a product of two integrals, one with respect to r, one with respect to theta. So I could take all the factors of r and move them over here. And then I just have I can keep them in here, move a cosine theta over here. So I'm integrating cosine theta from 0 to 2 pi, and then integrating with respect to theta, and integrating little r squared from 0 to big R, d little r. The integral of cosine theta from 0 to 2 pi is 0. The integral of sine theta from 0 to 2 pi is 0. So these two integrals will turn out to be 0. Similar thing happens. Okay. So just to write out what I did, at least in that one example, if I take this first integral, okay. So now this double integral is a product of two single integrals, but this second one is 0. And we also have, if I take, oh wait, that should be uxy. So now if I take this integral, dang it. Okay. Oh, that should be 0 to 2 pi. Okay. All right, so same idea. So I'd have r cubed. Then I have cosine theta, sine theta. So then the first integral is easy enough to evaluate, capital R cubed over 3. But for this other one, this is that's the same as this is a derivative of sine squared theta. Because you take a derivative of sine squared theta, you get sorry, you have a factor of 1/2. You get 2 sine theta cosine theta. So this is the exact derivative of one half sine squared theta. Okay. This you can see this by u substitution. If I let u equal sine theta, then du is cosine theta d theta. So now I can plug in limits into here, and they're both going to get 0 both times. So that also is 0. So now if we just look at what's left, so that's gone, that's gone, that's gone. We just have these two. Now, what happens when we have cosine squared or sine squared? So I'll show you what happens there for cosine. It'll be the same for sine. Okay. All right, so that'll be, so I'd have r cubed Now I have cosine squared theta. But I can write that using a half-angle formula. That gives us this. So what we're going to wind up with, when now we can actually carry out the integration. So first integral, we're going to get capital R cubed over 3. And then I'm going to get the cosine 2 theta will end up not making any contribution. So you're just going to get 2 pi times a 1/2. So that's going to be, so you get pi for that. So now we can fill that in for this integral here. And it'll turn out to be the same result for this one right here, because you'll just have 1 minus cosine 2 theta over 2. So then when we put everything together, that the average value on the disk, that's all we had on the left side, is equal to u at the center of a disk, plus we're going to have, by the time we sort out all these constant factors, the pi's will cancel. I'll have r over 6 times what's left, uxx plus uyy, but that's the Laplacian. At x0, y0. Okay. So similar interpretation that if the something seems off here. Okay. Yeah, here I got the radius squared over 6. Okay. Oh, I'm sorry. Who can tell me what my mistake is? Actually, it's the same mistake made twice. In an integral. This is wrong. What should it be?
R to the 4th over 4.
Oh, wow, my speaker volume was really low. But yes, I was able to hear. And yes, it is correct. It's R. It should be R to the 4th over 4. This is what happens. This is what I get for doing things unplanned. R 4th over 4. So that part is still 0. And then I have the same thing down here. Whoops. Okay. So then what you end up with is, okay. 4 over 4. Okay, so then I have R squared over 8. Okay.
Oh, Dr. Lambers.
Yes.
Is that sine squared theta or sine 2 theta?
Wait, where?
There, right, down, where you just corrected your R cube. Yeah, there.
Yeah, that really should be sine squared.
Why?
If I take the derivative of this, so I have 1/2, and then the 2 comes down, it cancels,
Mm-hmm.
and I have sine theta times the derivative of sine, which is cosine. which is exactly this.
Okay.
All right, putting it, if I make a U substitution I mentioned earlier, U equals sine theta, I'm going to have U du. That's, you integrate that and you get 1/2 U squared. Oh, I see what you mean. Okay, yeah, because, well, yeah, by instead of integrating, if you could rewrite this as 1/2 sine 2 theta by double angle formula. Is that what you were thinking?
Yeah.
Okay, but then we wouldn't be integrating. Okay. All right. Now, unless I've messed up somewhere else. Okay. All right. So now we have this. So same interpretation as before, that if Laplacian is positive at this point, then that means that U at the center of a disk is less than the average value on the disk. And similarly, if it's Laplacian, then U is greater than the average, and so forth. Okay, so I just want to show you how it can be worked out in higher dimensions. Okay. So the role that the Laplacian plays in various PDEs including ones that we've seen before. So heat equation. So the way to physically interpret this in light of what we just seen is that if the temperature is less than the average of temperature at neighboring points, that's going to lead to the Laplacian being positive, and therefore the temperature at that point is going to increase. Similarly, if a temperature is at a certain point is less than the average of temperature at nearby points, then that's essentially concave down, so the temperature will decrease, which makes sense because ultimately you'll get an average temperature in the end everywhere. Wave equation also features a Laplacian in however many dimensions you have. If the displacement is less than the displacement neighboring points, then you're going to have a greater acceleration up. Then just plain old Laplace's equation, which will be a focus of these last few lessons, that's just Laplacian equals 0. That says the average is always equal. Okay, this is not stated correctly. That U is always equal to its average at neighboring points. You think of this as a steady state solution. Like if I let, if the UDT is 0 here, then I'd wind up with UXX equals 0. So Laplace equation can be thought of as a steady state solution of like a PDE involving Laplacian, such as heat equation. Poisson's equation is almost the same as Laplace equation. We just have a source term. And it's used to describe electrostatic potential, where F is the charge density. Okay. And finally, we also have the Helmholtz equation. Laplacian plus a constant lambda times U is 0, where lambda is a positive constant. But you've seen this equation before when you use separation of variables in heat equation or wave equation. The spatial part ends up giving you this. It's in the case of one dimension of its ODE, but it also has its importance as a standalone PDE. Okay. Now, the problems that we will be seeing in lessons 33 and 34, solving Laplace's equation, will concern first a domain that is just a disk, like I've just been dealing with in 2 dimensions. And then later an annulus, so the region between 2 circles. So that'll be a modification of case of a disk. Now, when you're going to be solving a Laplace equation on a domain of that kind, it's definitely a lot more convenient to work in polar coordinates rather than regular Cartesian coordinates, and you have uxx plus uyy. So we need to be able to express the Laplacian in polar coordinates. That's what I'll focus on now. Okay. So here are polar coordinates that we use. X is r cosine theta, y is r sine theta. But it's also convenient to be able to express these relationships in the opposite direction, r and theta, as functions of x and y. So to be able to change, we need to be able to rewrite uxx and uyy in terms of derivatives of u with respect to r and theta. So we need to take derivatives of these relationships that we have here. So what we get, so for example, if I take a derivative of r with respect to x, then what that would give me, if I just go ahead and carry out the differentiation, that would be 1/2 x squared plus y squared to minus 1/2 times the derivative of what's inside here, and that's just going to be 2x. Now, if I simplify that, that gives me this. But I want to express that in polar coordinates. Well, x is r cosine theta. And square root of x squared plus y squared, well, that's just r. So that simplifies, then we get dr dx is cosine theta. Similarly, dr dy is going to be sine theta. It would all work out exactly the same way, except you'd have a y up here. On the other hand, what about take derivative of theta with respect to x? So here's where actually we need to use implicit differentiation instead of the explicit differentiation that I could use here. So if I take a derivative of both sides of this equation with respect to x, then what I would get is derivative of tangent, so that would be secant squared theta, then times d theta dx is going to be equal to a derivative of this with respect to x, but that's just going to be minus, so at y we treat as a constant, and the derivative of 1 over x would be minus 1 over x squared. So then what I could do is rearrange, and I get theta x on the left side, and then if I move a secant squared theta to the other side, that's going to be minus. All right, so y is going to be r sine theta. X squared will be r squared cosine squared theta. And then secant squared theta over here on the left side becomes cosine squared theta in the numerator on the right side. And now I have a whole slew of things cancel, and I end up with d theta dx is minus sine theta over r. And dr dy and d theta dy are worked out in a very similar fashion. That gives us this. And I can continue this process. Like I could take the derivative of, I have rx is cosine theta, so I can take a derivative of both sides of this equation with respect to x. So I'm going to get minus sine theta d theta dx. But d theta dx is minus sine theta over r. So I just put that in here. Let me use some parentheses here to make this a little clearer. And I get sine squared theta over r. And all of these others can be worked out in a very similar manner. So this will help me express derivatives of u with respect to x and y as derivatives of u with respect to r and theta. Are there any questions about these? So now I will first want to express ux and uy. So du dx would be du dr dx. You can think of like dr's canceling, plus du d theta dx. So you can think of d thetas canceling. So now I can just take rx and theta x from up here, so here and here, and substitute these in. So now I have du dx in terms of ur and u theta. And I could do the same with du dy. So then I can do the same to get the second partial derivatives of u. So working on uxx, if I take this equation right here and apply the product rule to it, I want to take a derivative of all of this with respect to x. So I get urx rx plus ur rxx. So product rule applied to this gives me these first two terms. And then product rule applied to this gives me the other two terms. And differentiating with respect to x. Now, what I can do from here, it's a little messy, is urx, I can think of that as ux with respect to r. Similarly, I can think of this as ux with respect to theta. Okay. Now I can take my previous expression. Well, actually, no, not the final expression. I'm just going to go ahead and use this. So I can dump that in for ux. urrx plus u theta x. Okay. Oh, that's all with respect to r. Okay. And then same over here. Okay. I have a typo here somewhere. Oh, okay. 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 So now, if I take a derivative of all of this with respect to r, here I need product rule, so I give urr, and then I have rx, and then rx again, so I have rx squared. And then here I'll have u theta r, which is the same as u r theta, rx times theta x, so we get it here. And I'm going to get that same term from over here, u r theta, okay, I have another typo. Oh, I see what I did. X theta. Dang it. Okay. So I have u r theta rx times theta x. So I have two terms like this that I combine. Okay. I think I may have just got myself into a notational pickle here. Okay. Yeah. I actually have this worked out in these notes in two different ways. And now and this is from like 7 years ago, and I was like, why do I have it worked out two different ways? And I think now I see why. Sorry. One moment, please. I seem to have a formatting error. Okay. All right. All right. I should know better than to try to fix my notes in the middle of class. But I can tell you that this final result is definitely correct, but I think I just have some steps glossed over in getting from here to here, because we have all of these terms are accounted for by what we have here. But if you just go ahead and carry out product rule on all of this, like this is going to give rise to 4 terms from doing that. This too also give rise to 4 terms. 2 of them will combine to give you this. And then this term and this term come from what do you have of product rule. But there are 2 additional terms that come from here that are not accounted for down here. And if I go to take a moment to write those in, all right, so that's okay. Actually, 4 terms altogether. Okay. So that'd be U R R X R. Okay. Plus U theta XR. And then from over here, I'm going to have UR R X theta plus U theta X theta. Okay. All right. Now, can anyone tell me why I actually do not need to worry about these terms, why they actually don't present a problem? Because what's happened here is, wait, sorry, they're not supposed to be included in this line. Supposed to be included in the next one. Okay. All right. Now, if I take everything that I got here and I fill in what Rx is, so Rx squared, I get cosine squared. I fill in all my partial derivatives with respect to of R and theta with respect to X. And also Rxx and theta x. If I fill in all of those things that I got from up here and fill them in, so everything from these terms, I get exactly this. So that would suggest that these terms must be 0. And they are 0. Can anyone tell me why these terms must be 0? Like, let's just focus on one of them. This term. Can anyone tell me why this term should be 0? Okay. R XR. So I'm taking R, derivative with respect to X, then with respect to R. But I can also, if I do it this way, that's the same as sorry, this editor is not cooperating at all. Okay. That's the same as dr, take a derivative with respect to X. Now I'll ask a question again. Can anyone tell me why they think why this term should be 0? What is the derivative of R with respect to R?
Oh, 1.
Yeah. Derivative of 1 with respect to X will be 0. So that explains why this term is 0. And it also explains why this term is 0. Same thing. You have theta with respect to theta. Over here, you think of, okay, this derivative of theta with respect to R, or R with respect to theta. R and theta are independent variables. So their derivatives with respect to each other would be 0. So that's why all 4 of these terms end up being 0. Another way to see it in the case of theta xr, well, d theta dx, I have that up here. D theta dx is Oh. Shoot, it didn't work out the way I wanted to. Sorry. Okay. Oh, this is another way to see why RXR is 0. dr dx is cosine theta. You take a derivative of this with respect to R and you get 0. Okay. RX and so I'll take a look at these other terms here. Okay. All right. Now, and here we have UYY worked out in a similar manner. But if you put everything together, UXX plus UYY, okay. Then from here, notice we have cosine squared URR plus sine squared URR. Here we have cosine squared plus sine squared equals 1, and that's why we end up with URR down here. Similarly, here we have these two terms. This one and this one will cancel. This one and this one will also cancel. Here too, we again have case of sine squared plus cosine squared equals 1 that causes these terms to combine. And that's why you don't see any cosine or sine thetas in the final result. So this is Laplacian in polar coordinates. So that's what we use when solving Laplace's equation in polar coordinates in later lessons. Laplacian is also often used in cylindrical coordinates. And so this is for 3 dimensions, where z is just z. So we add on a UZZ term. This accounts for UXX plus UYY. And then spherical coordinates is this is a full Laplacian in that coordinate system. The last thing I want to mention is this is a easier way, and I will admit now, and my apologies, I should have done it this way to begin with. That's what I guess what happens when you come back to a class after teaching it 7 years later, 7 years ago, and you forget what stumbling blocks you had back then. Here, UXX, this is my expression that I had before for du dx. So if I go back up here, here's my du dx. So I just go ahead and dump that in here. I want a derivative of this with respect to x. But taking a derivative of anything with respect to x is the same as taking a derivative with respect to r times rx plus derivative with respect to theta times theta x. So by using the expressions I got for ux before, I can just go ahead and here I already have derivatives with respect to only r or theta. So now I'm no longer mixing partial derivatives, which is kind of an explanation for a mess up above. So I take a derivative of this with respect to r, and this is what I get. And then Rx was determined before to be cosine theta, so I fill that in here. And then derivative, same thing with respect to theta, and then here's my theta x. So then I can go ahead and work all this out and get certain terms canceling, and I get the same result as what I had up above. So yes, so this is definitely, I would say, an easier way to see how UXX comes about in polar coordinates. And it all boils down to using this application of chain rule twice. So differentiating anything with respect to x is that with respect to rx plus derivative with respect to theta x. So you apply that first to get this expression for ux. Then you apply this rule again, except you're applying it not to u, but to du dx to get uxx. And so then this framework used again gets you to the expression with less with less hassle than what we saw here. Okay, so that Laplacian you see in polar coordinates, this is what we'll be working with going forward. Because of the domains we'll be considering for our PDEs, Laplace equation on a disk or an annulus, or polar coordinates is more convenient. Okay. So now that I've fairly made a mess of things, does anyone have any questions about this or homework? Okay. So we'll continue with Laplace's equation on Wednesday, Monday, and once I have more information about the test, I'll be able to pass that on. So I will stop recording at this point, and anyone who has questions can stick around.